So section 4.3 talks about paths. There's a couple of different ways. Because we are talking about different representations of a relation, I'll write these down again. The different representations of a relation. If I just refer to it as a relation, I'm talking about a set of ordered pairs. Remember, it is ordered because the order in which they appear matters. A, B is different than B, A because order matters. It's set, so we use the set notation with the curly braces. Then we also have a matrix of a relation where each ordered pair so each ordered pair in the relation is mapped as a 1 in the matrix. If the ordered pair doesn't exist, then there is a 0 at that position in the matrix. And then finally, we were doing the digraph of the relation, which has nodes and arrows, where the nodes are elements in the original set. All of the elements in the set are marked down as nodes, and then the arrows represent ordered pairs. So let's talk about paths. I know that when we ended our conversation last time, we were talking about the in degree and the out degree of each one of the individual nodes, right? And so we would list out all of the nodes, and then we would list out the in degree and the out degree. So how, from a digraph, specifically from a digraph, how can I determine what the in degree is from a digraph? The in degree of a node.
The arrows going in.
Yeah, that means the arrow's going in. So I just look at a node, node 1, and I see all the arrows that are coming in, and that's the in degree. And I do that for each and every single one of the nodes in a digraph. So what is the out degree of a node? Yeah, just the arrows coming out. I look at a node, I see all of the lines that are coming out of it, the arrows that are coming out of it, and I mark that down as the out degree. So now what we need to do is discuss paths. So a path is a finite sequence of arrows where the starting node for each arrow is the ending node of the previous arrow. So a path, it is a finite sequence of arrows. And then we have to define it as the starting point for each arrow is the ending point of the previous arrow. There we go. So this is the path as it was defined in a digraph. So let's see what this might look like. So let's say, for instance, that I had some ordered pair AB. I can tell if this is just a minimal portion of this that there is a node A and there is a node B. And that the fact that AB is an ordered pair means that there is an arrow, a directed line, indicating the direction of the relation. So the arrow goes from A to B. So let's say, for instance, that if I had this digraph, I'm going to say the digraph is 1, 2, 3, 4, and 5. Let's just imagine that this is over the set 1, 2, 3, 4, and 5. And that I had a relation over that set. The relation is a set of ordered pairs, a subset of the ordered pairs. So let's just say that we have a relation. I'm pretty sure that we have seen this relation before. We have the relation 1, 2. and I have 2, 3, and we have 4, 3, and I have 3, 5, 5, 4, 5, 5. So we have 1, 2, 2, 3, 4, 3, 5, 4. Oh, and 1, 4. We're missing 1, 4. So how many ordered pairs do I have in this particular relation? 7. 1, 2, 3, 4, 5, 6, 7. I think 7. All right, here we go. So what I'm going to do is I'm going to create the digraph of this relation. So if there are 7 pairs, there should be 7 arrows. The arrow indicates an ordered pair. So there is going to be an ordered pair. There it is, 1, 2. So I'm going to draw the line from 1 to 2. Then there is a line from 2 to 3, so I'll draw the directed arrow from 2 to 3. Then we should find 4 to 3. Then we should find 1, 4. Find 3, 5. 5, 4. And then finally 5, 5. How do I indicate 5, 5? Yeah, so we're just going to have an arrow from 5 to itself. All right. So a path. We define path as a sequence of arrows where the start node for each arrow is the end of the previous arrow. And I'm going to define it as a path, so we'll call it path. There are and it is a finite, defined as a finite sequence of arrows. So I'm going to say maybe there's path 1. So if I started at the first node, there is an arrow from the first node to the second node, correct? And then there is an arrow from the second node to the third node, and I see there's also an arrow from the third node to the fifth node. That is one particular cycle. It would be written as 1 to 2 to 3 to 5. I can see it going 1 to 2 to 3 to 5 if I just follow the directions of an arrow. That is one of the paths through this particular digraph. There is another path through the digraph. Another path through the digraph, I'll call it the second path, that goes 1 to 2 to 3. There is another path through the digraph that goes 1 to 2 to 3 to 5 to 5 to 4. So I would say that there potential exists that there are an infinite number of paths. But the definition of a path is that it is a finite path that does have a start and it does have an ending point. And the fact that it has to map out where the starting point is aside from the beginning node, the starting point is the previous point for the last arrow, so that I can map out, follow the arrows through in a finite sequence of nodes. Yes, sir?
Can it go into like a repeating like infinitely where it goes like 1 to 2 to 3 to 5 to 4 to 3 to 5 to 4 to 3 to
There is a finite number of nodes.
Okay, what if it so if it eventually ends?
It would have to eventually end, and you would have to show that eventual end. Because this one, there would be another path, a separate and distinct path, 1 to 2 to 3 to 5 to 5 to 5 to 5 to 5 to 5 to 4.
Okay.
Or 1 to 3 to 5, 1 to 2 to 3 to 5 to 5 to 5 to 5 to 5.
So it doesn't matter if it repeats as long
Right. It is defined as a finite sequence of nodes. It has to have some beginning, and it has to have some some end. 1 to 4 to 3 to 5 is another path. Excellent. So there is a path 4. That is 1 to 4 to 3 to 5. Absolutely. Yes. That is a separate and distinct path. If you'll notice, there's probably an infinite number of paths here. An infinite number of paths. But a single path must have a beginning and an end. Yes, sir?
So the relations that you have up there, are those just stuff that's generated or you just give to us? Or is
Yes.
that's not something you like determined, like looking at it?
Did I no, no. That was a little bit like when we were drawing truth tables before, and I would give you X, Y, and Z, and we would map out the X, Y, and Z, and then I would say, based upon X, Y, and Z, here is an output column. And then we tried to figure out what the Boolean expression was that was generating that output column. Yeah, so consider this as just the output column on a truth table. I could call it randomly defined, or I could probably find a function. We were discussing a function that might generate it. Because I know before when we were doing, when we were generating the relation and the ordered pairs in a relation, we actually defined the relation as a function. Although some of you said it wasn't a valid function because it had two values of x. We're generating, the same value of x was generating two separate values of y. So yeah, this is a random selection of all possible subsets of A crossed with itself. So the relation is defined as the subset of the cross product of one or two matrices.
How do we know when a path ends?
How do you know when a path ends? How do you know? You can just decide. Here we have three separate paths, and they're
We can go.
the idea is that I'm never going to say something like list all possible paths through a digraph, because that would be an infinite number of paths. I might say list two paths through a digraph beginning in node 2, because there is going to be another path that starts at node 2. Can somebody tell me one path that begins at node 2? 2 to 3 is indeed a path. 2 to 3 is a path. What about another one? Is there another one that begins at 2?
2, 3, 5.
2 to 3 to 5. Excellent. There's another one. 2 to 3 to 5 would be another one. 2 to 3 to 5 to 5 would also be another one, because 5 continues. So there you go. So if I were to find what a path was when it comes to a sequence of ordered pairs, this was a path as defined by a relation. Excuse me, by a digraph. So if I were to define a path in terms of a relation, I should be able to tell that it is a finite sequence of ordered pairs, where the first value in each pair is the same as the second value in the last pair. It's a finite sequence, once again. All right, fine. We'll put this down below so I have a little bit more room. I think I was running out of room to write this. So it's a finite, once again, finite sequence of ordered pairs where the first value in each pair is the same as the second value in the previous pair.
That finite looks oddly not like finite. That first like vertical line right there kind of looks like fuck. No, the I.
Is that not how you spell finite?
That is.
Is that better?
Yeah.
Because I still don't see what you were saying, but if it was offensive, I should probably erase
So
it.
just the way they connected in the white spaces and stuff, when you look
Oh,
at it
the
back
T to
there,
the E.
it's-
Okay, is that better? Is the same as the second value in the previous pair. All right, so let's see if we can find a path. I'm going to define a path. I see that I have at least, it looks like 7 or 8 of them listed above. And so if I wanted to indicate a path in terms of a relation, I might say, I will call this path 1. I can actually write this as a set of ordered pairs. So I'm going to repeat this path right here is a set of ordered pairs. And I can see that that set of ordered pairs is going to be 1, 2, 2, 3, 3, 5. And now let's do if we can do this one. The path 2 is a set of ordered pairs. Would be 1, 2, and 2, 3. So I can write the paths as a set of ordered pairs. Path 3 from above is going to be let's say that it is 1, 2, 2, 3, 3, 5, 5, 5, and 5, 4. Remember, it is a finite sequence of ordered pairs. So I should be able to look at a relation, and perhaps, just perhaps, from looking at the relation up here, let's see that if I can do this by looking at the relation, this was the relation here. Just by looking at it, can I find another path, let's say that begins at 5? I'll call this path A. So if it has to start at 5 and goes somewhere, so what would be one possible potential beginning place for an ordered pair and a path that begins in 5? Well, I'm hearing Juan say 5, 5. So what else would be next? 5, 4. Say it again.
5, 4.
5, 4. Somewhere else? 4, 3. 3, 5. And then 5, 5. All right, we're going to stop there, but you get the idea of what I'm doing. So the idea is that this first value in the second pair has to match the second value in the first pair. So the 5 in the second ordered pair has to match the 5 in the first ordered pair. When I move to my second ordered pair, that 4 has to match the next value in the next ordered pair, or I guess if we work our way backwards, just to make sure that we are defining a path. It's easier for me to define a path through a digraph because I can match it visually with the arrows, but it is possible for me to find a path through just a set of ordered pairs. And as always, it is a finite sequence, but I am betting that there's an infinite number of paths through this particular relation. Just given the fact that I am seeing something called a cycle, and we'll come back to what a cycle is in just a minute. So the next thing that I want to know about a path is that every path has a length. And the length of the path is defined as the number of arrows in the sequence. Many students mistake it for the number of nodes. It is not the number of nodes, it is the number of pairs in the sequence. And the way I determine the number of pairs is that is the definition of the arrow. The arrow defines a single set of pairs. A to B, there's an arrow going from A to B. Therefore, I count the arrows, and that will tell me the length of the path. So let's come back up here and look at some of the paths that we have identified. Path 1. What is the length of path 1? Well, if I count 1, 2, 3, I can see that there are 3 arrows. What is the the length of path 2? It's going to be 2 because I see 2 arrows. What is the length of path 3? 5. It's going to be 5. 1, 2, 3, 4, 5. So if there is one mistake that students make, it is counting the number of nodes. If you count the number of nodes, 1, 2, 3, 4, you might believe the length of this path is 4, but it's not. It is 1, 2, 3.
The length is
always be the case?
Will that always be the case? Yeah, that would always be the case. So the path is literally the number of ordered pairs. So if I come back and I look at paths as defined as ordered pairs, what is the path of this one? Excuse me, not the path. What is the length of this one? 3. This one seems to be a whole lot easier to find. What is the length of this relation, or this path? 2, and the length of this path? It's 5. So it's a whole lot easier to distinguish the path when I look at it as a set of ordered pairs. It's a little bit, but not much, just a little bit more interesting when I try to define the length of a path when I flat out look at the digraph, or the sequence of pairs through a digraph. So every single path has a length. It's just the number of edges, arrows, also called arrows. All right, so the next thing that we want to know about is a cycle, which is why we had to come back to 4.3 so we could talk about this thing called a cycle. And a cycle is defined as a path that begins and ends on the same node. It's called a cycle because it returns to its starting point. So if we come back to our original, let's see if we can define some cycles. I'm going to come back up here and see if we can define some cycles based upon this digraph. As a matter of fact, if you don't mind, I'm going to steal this digraph so that we can move it down a little bit. I'm going to copy and paste it. I'll move it down here, and let's see if we can find some cycles through this particular digraph. So let me put it here. So the most trivial of all cycles, I'll call it cycle 1, the most trivial of all cycles would be 5 to 5, because 5 is looping back in on itself. That is the most trivial and the shortest of all the cycles. All right, you're going to have to talk slower than that. Tell me another one.
Any of them from 5, 4, or 3?
Okay, just give me one. Just give me one.
3, 5, 4, 3.
You're going to say it again?
3, 5, 4, 3.
3 to 5 to 4 to 3. There's another cycle. Here is another cycle. I'll call this one cycle 3. 3 to 5 to 5 to 4 to 3. Cycles are finite. They have to begin and end on the same node, but there are most likely an infinite number of cycles. Doesn't mean that there is always a cycle in a given relation. The potential exists that a relation does not have a single cycle because there is no way to get from a node back to itself. Here is another one. 3 to 5 to 5 to 5 to 4 to 3. So cycles begin and end on the same node. Cycles also have a length. Once again, it's the number of edges. The number of arrows. We call them arrows or edges. The number of pairs. All right, so let's see if we can define the length of this cycle. What is the length of this cycle? 1. Because there is one edge, one arrow, one set of ordered pairs. What is the length of this one? 3. The length of this one? Yep, the length of that one is 4. I see 4 edges representing 4 ordered pairs. The length of this one right here? 1, 2, 3, 4, 5. Very good. So we have paths, and paths have a length. Paths have a beginning and an ending place. The cycle is a specialized type of path. That it is a path, a finite set of ordered pairs with some defined begin and some defined end, but a cycle is a same defined begin and end, and they both have lengths. So given this particular, let's see if we can come up with another one. Because one of the things that I might ask you to do is, I don't know, list paths. I might ask you to list all paths of length 2. I'll give you a length. So let's start with some set A that includes 1, 4, and 5. From that, I'm going to define the digraph of the relation. If I'm going to draw a digraph, I have to have all 1, 4, and 5, all of the nodes in the original set, and then I'm going to define a relation that looks like this. All right, there we go. That is, the relation is defined by, the relation over the set is defined by a digraph. Remember I told you there are 3 representations of a relation. Set of ordered pairs, digraph, matrix. So here is a relation as defined by a digraph. So then I'm going to ask the question, let's list all paths of length 1. Let's list all paths of length 1. Once again, when I'm trying to list all of anything, I like to try, to the best of my ability, to be as organized as possible. So let's list all paths starting at node 1. Paths of length 1 starting at node 1. 1 to 4 and 1 to 5. Are there any others? All right, so now let's move to node, not node 2. Let's move to node 4. 4 to 4? 4 to 1? Any others? All right, so then the last one is 5. Let's list all paths of length 1 from 5. Excellent. So this is a listing of all paths of length 1. Now the nice thing about all paths of length 1 is this is actually a representation of ordered pairs, right? So in theory, all paths of length 1 is a set of ordered pairs, which means that from this I could, if I wanted to, generate the ordered pairs in the relation. And the ordered pairs in this relation are going to be 1, 4, and 1, 5. It's going to be 4, 4, 4, 1, 5, 5, and 5, 4, because that is literally what an ordered pair is. It is a path of length 1. And I said I could tell if I was getting to, I like to check my work. When I was mapping minterms to Carnot maps, I wanted to make sure that I had the right number. So if there were 7 minterms, how many ones should be on the Carnot map? 7. 7 minterms on my truth table. There should be, mapping to the Carnot map to begin with, there should be 7 ones. So I said before, if there are 7 ordered pairs in my relation, how many lines should there be on my digraph? So I'm going to ask you the question backwards because we started with a digraph. How many lines are on my digraph? There are 6 lines. Does everybody agree with that? 6 lines? 1, 2, 3, 4, 5, 6. If there are 6 lines on my digraph, how many ordered pairs should be in my relation? 6 pairs. So we have 1, 2, 3, 4, 5, 6. That means that I have enough of them. It doesn't mean I got them right, but it does mean that I have enough of them. And I like to check my work. So what happens if the next thing that I ask you is, now I want you to list of length 2. How am I going to go about listing all paths of length 2? There you go. I'm going to try to be as organized as possible. So let's start at node 1. I'm going to write it up here so that hopefully we have enough room. So I'll even put it up here, all paths of length 2 starting at node 1. All right, we'll do it down here. That's making me nervous. All right, so tell me a path of length 2 beginning at node 1. 1, 4, and 1. Are there any others? 1, 4 to 4. Are there any others? 1 to 5 to 5. And then 1 to 5 to 4. Any others? Paths of length 2, starting at node 1. If I ask you, tell me all paths of length 2 through this digraph, you can just randomly start willy-nilly grabbing paths of length 2, but how do you know if you have them all? Try to be slightly more organized. Let's look at node 1 first. All paths of length 1 from... So the way that I can do that is I noticed that you guys went to node 4 first. 1 has 2 out degree. The out degree of node 1 is 2. That means it goes to 2 places. So I'm going to start at the first place, see where it goes, and then does it go anywhere from there? And if it does, it's path of length 2. Then I'm going to go to the second out degree, the second place it goes to, which you guys found was 5. 1 goes to 5. Excellent. From 5, does 5 go anywhere? And if it does, that is also a path of length 2. So let's repeat the process with 4. Paths of length 4 from node, paths of length 2 from node 4, which means that it's probably going to start at node 4. Does node 4 go anywhere? Okay. 4 to 4 to 4. Say it again. 4 goes to 1. 4 to 1 to 4. 4 to 4 to 1. Are there any others?
Yes, 4 to 1 to 5.
4 to 1 to 5. Are there any others? Okay. We're doing good. The next thing, if I say list all paths of length 2, I need to pick up the last and the final node, node 5. Are there any paths of length 2 coming out of 5? How many out degree is in node 5? I need to check each one of those places that it goes. Say it again.
Again, we will have 4 paths.
I'm looking at paths of length 2, so tell me a path of length 2.
Okay, 5, 5, 5.
5 to 5 to 5. Okay? Anything else? 5 to 5 to 4.
5 to 4 to 4.
5 to 4. Does 4 go to itself? 5 to 4 to 4.
And 5 to 4 to 1.
Then 5 to 4 to 1. Are there any others? Excellent. So we can list all paths of length 2. If I were to turn around and say, tell me all paths of length 3, all paths of length 4, all paths of length 19. I would try to be as organized as possible, and I would start at an individual node, and I would start mapping through paths. So let's just look at some cycles. Not only do we want to know paths, but sometimes let's just list some cycles. Because I don't want to say cycles of length 12 or cycles of length 1. Let's just list some cycles. Tell me some cycles. Are there any cycles from node 1? 1 to 5 to 4 to 1. Are there any others?
1 to 5 to 5 to 5 to 4 to 4 to 4 to 4 to 1.
All right. You're definitely getting into the spirit of things. All right, so how about 4? Are there any cycles from 4?
4 to 4.
That's a trivial cycle. Length 1.
4 to 1 to 5 to 4. 4 to 1 to 5 to 5 to 4. 5 to 5 to 5 to 5 to 5 to 5.
Excellent. You are in the spirit of it all. All right, how about node 5? Are there cycles from 5?
5 to 5, 5, 4, 1.
That's not a cycle.
5415.
5415, excellent.
5, 4, 1, 5.
Excellent. So cycles have to begin and end on the exact same node. So this is just a small listing of cycles. So we find out that digraphs have paths, and paths have length, and they have specialized types of paths called cycles. Cycles also have lengths. We also find out that if I wanted to, I could list all of the paths of a given length. I probably, with more effort, list all cycles of a given length. The potential may exist that there is not a cycle of length 1. The only thing that is going to allow for a cycle of length 1 is if a node loops in on itself. If it doesn't, I can still find cycles, potentially find cycles, but none. If there are no nodes that loop onto themselves or arrows that come back onto the node.
If something loops to itself, then there'd be like infinite.
There would be. And I'm saying if there is a cycle of any length, there's going to be an infinite number of cycles, because I could just keep looping through that exact same cycle again, once, twice, 3, 4 times. So there would be an infinite. If there is a cycle, there is an infinite number of cycles. Yes, sir.
If we have to find like how many cycles had like the length of, or how many cycles there were like length of 5 or whatever we did, is there like an easier way than listing them all out, like a mathematical way to do
What
it?
we're going to find out is we're going to find out we can find paths of a specific length. That's going to come in this module, but not in this chapter, or not in this section. Because, yeah, it would be nice to know, is there a way for me to determine all paths of length 2, all paths of length 3, without having to do it this way through a digraph? There absolutely is, yeah. So as I said before, what I really ultimately want you to be able to do is to move between the 3 representations of a digraph, a set of matrix of a relation, the 3 representations of a matrix. So let's try another example. And we're going to see if we can find all 3 representations of this thing we're calling a relation. Let's say, for instance, that I have some set A that is 1, 2, and 3, and that the relation, as defined by a set of ordered pairs, is going to be some subset of the cross product of A with itself. It's going to contain 1, 2, 2, 2, 2, 3, and 1. Some subset of the cross product of A with itself. So let's see if we could find the matrix of the relation. So the matrix of the relation, if a relation is the subset of the cross product of a matrix with itself, product of either a matrix with itself or a matrix with another matrix. So if this is a 3 by 3 and this is a 3 by 3, we're going to find out that the answer is a 3 by 3. And we said that the matrix, the way that I define the elements of a matrix, is each one of the ordered pairs maps to a position in the matrix. So if there are 4 ordered pairs, how many? 4. I'm not guaranteeing they're in the right place, but they're 4, no more, no less. So let's map them. The rows always represent the first matrix, and the first matrix is A. A contains 1, 2, and 3. The columns always represent the second matrix, and since it's still A, that means the columns represent 1, 2, and 3. This is position 1, 1, 1, 2, 1, 3. This is position 2, 1, 2, 2, and 2, 3. This is position 3, 1, 3, 2, and 3, 3. So I just did that to help remind myself of where each one of these positions are. Now I'm going to map the 4 ordered pairs to my matrix. So I need 1, 2. I'm pretty sure the 1, 2 is right there. The mapping, just like a Carnot map, says if the min term exists, then I map the 1 to the kernel map. Same thing is true as an ordered pair. If the ordered pair exists, it maps as a 1 to the kernel map, or to the matrix. Now I'm going to look for 2, 2. It looks like this is 2, 2. I'm going to look for 2, 3. There is 2, 3. And then I'm going to look for 3, 1. So I see 4 1s. I am going to fill in all of the remaining zeros just so I don't get lost in my horizontal challenge. I can't get a horizontal line going on to save my life, so I'm just going to fill in the zeros. So now I have defined the matrix of that relation. Once again, if there are 4 pairs, there should be 4 1s. Critically important that I have all 4 of them. Not saying they're in the right place, but I am saying that I have all 4 of them. So the next thing that we're going to do is the digraph of the relation. So the digraph of the relation requires nodes for every element in both sets. Since I only have one set, means I need a 1, a 2, and a 3. Here is a 1. I'll even make them just a little bit bigger. All right, so this is going to be 1. I'll put the here. I can put them in any ordering that I want to. I could have put 1, 2, 3 in a straight line. I could have put them in a horizontal or a vertical line. I could have put them on a diagonal. I could have made a star. I don't know if I can do a star out of 3 little circles, but I can draw them in any configuration that I want to. It's just a little bit easier to do it in some type of a circle because I'm going to have to begin to connect them by lines. Because now what it says is if the nodes, also called vertices or the vertex, the vertices indicate or represent the individual elements of the set, all of the elements of the set. And since set A contains 1, 2, and 3, then edges or the arrows represent ordered pairs. So now what I'm going to do is I'm going to map ordered pairs. I'm going to come back to 2, which means there had better be an arrow from 1 to 2, indicating the direction of the relation. 2, 2, from 2 to 2. 2, 3 is an arrow from 2 to 3. And 3, 1 is an arrow from 3 to 1. It is a beautiful thing. I have the digraph of the relation. If there are 4 pairs and 4 1s, there should be what? 4 pairs in the relation, 4 1s in the matrix, 4 arrows. Because the arrows represent ordered pairs, there had better be 4 of them. 1, 2, and there are 4. I'm not saying I have them in the right place, but I have 4 of them, so I'm on the right track. So I should be able to move between these 3 representations of a matrix, of a relation, and from there, can somebody tell me, can somebody give me a path? I'll call it path 1. Can somebody give me a path through either the digraph or the relation as defined by ordered pairs? 1, 2 to 3. 1 to 2 to 3. There it is. I see 1. What is another path? 2 to 2. And so as we said, paths have length. What is the length of this first path?
2.
And the length of the second path?
1.
1. Cycles. Let's see if we can find a cycle. Through either the digraph or the relation. It's a lot harder for me to find cycles through a set of ordered pairs because the ordered pairs would have to come back to the same place, and now I'm going to have to just start moving through my head. But a digraph is a visual representation, so can somebody tell me a cycle through the digraph?
1, 2, 3, 1.
1 to 2 to 3 to 1. Is there another cycle? 3 to 1 to 2 to 3. It'd have to end. So cycles also have length. What is the length of this cycle?
3.
3. Remember, we are counting edges. All right, let me do that in another color. We are counting edges when we count the length of anything. 1, 2, 3. So what is the length of my second cycle?
4.
All right, 4. So that would be 1, 2, 3, 4. So the length here is going to be 4. All right, does anybody have any questions about this? Questions, comments, thoughts? All right, it's your turn.